Okay, so we are now also recording. Okay, so let's go for it. Today is our third session, if I remember correctly, about computer vision, okay? And we are going to be speaking about NumPy today. So let's see a calendar, for example, here. We have today is June 2nd. We are going to have another session next week. In next week's session, I will be addressing some of the tasks in the second project from task 4 onward. I will not, of course, be giving solutions or anything, but I hope to give you some structure on the things that you have to do. The initial tasks are pretty basic, pretty easy, I think, and with last week's session, the first session, and today's session, everyone should be able to complete them without too many problems. Today we will address the manipulation of images efficiently using NumPy, which is a big part of this, because if you don't do it with NumPy, as we will see in a second, things will get very slow and you will not be able to complete most of the tasks in a satisfactory manner. So today is NumPy. Next week is more about the structure of tasks 4, 5, 6, and onwards, which are a little bit complex, meaning that they are not super difficult to do or anything, but they use different things of the things that we have already been working on. So they will be using, of course, opening images and dealing with them as NumPy, but they will also need some algorithmic understanding to see what you have to do, what steps do you have, which one is first, which one is second, how you combine the different parts. Some of them also will use pandas, which you already saw a little bit, we already saw a little bit of in in project number 1. So next week will be about more of these structural things, overview of the most complex tasks. So far, I have received some input from you, but not a lot. So don't sleep on it, okay? Next week, we have this, let's say, general session about the structure of the most complicated tasks. Following week, we will have, like in the first project, a questions and answer session. And if there are not many questions and answer, I will talk about some advanced material for those of you who have already finished, that there are some people who have already finished. And 17 is the deadline. Okay, so the deadline is 2 weeks and 1 day away. So don't sleep on it. This is, as all the projects, about 1/3 of the final grade. I think so far the results have been pretty good, but I don't get lots of communication from many of you. Some of you have been taking advantage of the feedback, and I'm super happy about it. The ones that have not, please do. It will help you, okay? If you get the hang of the NumPy manipulation, of the general way to work with images, this project is not difficult, but it has lots of tasks, okay? You don't have to complete them all, but if you do complete them all, you will learn more and you will make sure that you get as many points as possible, okay? So please, feedback, use it. Okay, so I will be working mostly with this second notebook from the image processing course, this bonus unit about using NumPy to process images and seeing images as NumPy vectors or NumPy arrays. Usually they are called arrays. I will be using the two words indistinctly, okay? Sorry, I have made a special notebook so that we could all see. Here it is. And we also had a another calendar here. Okay, so this is a notebook where I have just started by copying some of the code cells from this notebook that I'm going to be using. Basically, I have started by copying the imports, and we are going to be using mostly CV2, time it a little bit to compare the times of different things. And as usual, matplotlib, but today we are going to be using NumPy quite a lot, okay? I also left in the pandas import, although we're probably not going to use it too much, maybe a little bit at the end of the session. I downloaded everything from Colab as usual. Remember that you can check the data in your computer if you want. You can just download it from here. For example, you can come here and download, or you can just use the link from here, copy it and paste it to your browser. Someone was saying that they had trouble with this DL0 and that they used something else. Let me check that for you in a second, because we have it in Slack in the image processing course. Remember, that's another place where you can go and get some input, okay? Okay, so someone was saying, if you change this DL1 for, sorry, this DL0 here, again, I changed that. This DL0 here for DL1, then you will also get the download. In my experience, if you just erase this from the ampersand forward, that should also work, okay? In case you want to download the data to your computer and check it. If you have a GPU computer, you can also use that in project number 3 that will use the same data to do some faster experiments. Everything can be done in Google Colab. Google Colab GPU is a little bit slow. So if you have access to a GPU, that can help save some time. If you're in the Faculty of Science, I can also provide access to some GPU computers from the university. I'm sorry, I don't know the situation in Yonezawa, okay? If some of you are really interested in that, let me know and I will try to find out. Okay, so we have all this data downloaded. This initial cell just downloads everything that we can see here, the file and the folder and file structure that we can see in Colab, and it is explained in detail in project number 2. Okay, I just downloaded everything, copied some of the initial cells where we have the definition of the data path and a couple of functions to read mosaics and binary masks. And these, of course, can be very, very useful for the initial tasks of project number 2. Although I don't think I need to detail exactly how, okay? I'm going to start here, okay? Cell is already running. It should not be. Okay, so this got killed somehow. Let me see. Sometimes the runtimes in Colab get a little bit stuck, but I think now everything should be fine. Okay, so what I have done here is just start a computation. I have read one file, one binary mask. I will look at it in detail in a second. And I've just started a timer that counts the black pixels, something that you also might remember from task number 3, is it, I think? And just examines, looks at every pixel in an image using a for loop and the image shape. Very simple, exactly as we had been doing things in project number 1, works perfectly. Only it takes a while, okay? For example, in this computer, it took 37 seconds to process one image, one single mask, okay? Why is that? Let's see. I have downloaded the data to my downloads folder, and let's open with GIMP, for example. What was the data that we were looking at? This was S201. So inside 2, we are opening the species 01 mask, binary mask. Okay, we open it with GIMP. Will take a little while, and here it is. Okay, remember the importance of annotation. What we are talking about here is always data science, but we cannot do any data science unless we have a team of people willing to provide the expert knowledge. For example, in this case, we're dealing with forest images. Okay, I can even open the mosaic here as a layer. It will again take a while because these images are pretty big. Okay, so we have this image, and here we can have a look at the superposition. So this annotation is telling us the position of these trees of species 1. Somewhere else we have the names of the species too. Okay, but for us, suffice it to say that this is the first species that we are considering. Okay, so let's zoom in, and we have some of the clumps of trees corresponding to those species, okay, to these species. That took that person that I told you about last time, Sarah Brandt now, I think something like 1 hour per mosaic to annotate. Okay, maybe this one was a little bit shorter because there are very few trees, but I'm not sure because you have to go and check every single tree around the mosaic and see what species that one belongs to. Okay, so check, is that from the species I want to annotate? Yes, then I have to go and annotate it. Okay, there is, now that I see it, probably some wrong annotation here. Okay, because this is not a tree and this is in the mask and this is very small. Okay, so interesting. Okay, manual annotations have that problem. Maybe they get some small mistakes. We will be dealing with that in task 5, I think, from project number 2. Okay. Once we have this expert annotation, we need to process it. And what I wanted to show you here, let me close this and let me make this again fully solid. These images have lots of pixels, okay? So I can zoom in, for example, so that we can see the border of one of these 3 regions, okay? And that's how far I have zoomed in, okay? Here everything is black, and here, around here, I have the border, okay? So that's how many times I have had to zoom in. I can, for example, just check the number of pixels. As image properties, this has 11,000 times 9,000. Okay, let's actually check how much that is with a simple calculator. 9945. So that's in English, if I'm cutting it correctly, 113 million pixels for this simple image for one of the masks in one of the sites. Okay, so that is why running this is going to take at least 37 seconds. If I'm only doing something as simple as checking the pixels and counting the number in each position and seeing if they are 0 or not. That's completely unfeasible for any kind of serious computation. You have to spend 37 seconds per mask. I have potentially 47 masks per site, and I have 13 sites. So that's just not going to cut it. Okay. As we already saw with functional programming, Python has one very good strength, that it allows us to process data in parallel. So not like this with a general purpose for loop that runs only in the CPU, in the processor from the computer, but in one single processor from the computer, but Python allows us to process things in different processors at the same time. Okay, and it has many ways to do it. One is to use maps, for example. And in project number 2, I asked you to do this, essentially the same thing with a map too, and see if there is a difference or not. But not only that, Python has dedicated libraries to speed things up by parallelizing in the CPU itself and also in the GPU. Okay, what's the difference? The CPU is the part of what's called the central processing unit, the CPU, that's in the motherboard of your computer, and it has several small but very powerful processors that can do very, very complex calculations. Okay, so nowadays, all of our computers have at least 4, sometimes 8. Unfortunately, Colab machines only have 2. Okay, so the final part of project 1 could not be really seen. Some of you did it, and then you need to run that part in your own computer with more processors. So those processors can do very, very complex tasks, very, very general tasks. And if we use them in parallel, more than one at a time, then we get a significant bump in speed. And we saw that in project 1 by using functional programming that runs in parallel, by using list comprehensions, dictionary comprehensions. Okay. NumPy will also use the same trick, this capacity to run in parallel. There is a second way to speed things up, which we will see from project number 3, which is running things in the GPU. The GPU is the graphics processing unit, and that's full of processors. It has literally thousands of processors that are very, very simple and very, very stupid. They cannot do complex computations. They can only do simple additions and simple multiplications of numbers. What stands for simple matrix computations. Luckily for us, all we need for deep learning are a huge lot of very simple matrix computations. And we will explain that in detail in the third part of the subject. So in order for our code to run faster and be able to process these huge quantities of data that are present in even the simplest of images, okay, sorry, I have the simplest of images here, okay? So even this just black and white image that has, because of the resolution that we're working with, and we need to work with that resolution because we want to find complex patterns, the species of the trees come sometimes down to the texture of the leaves that we can see a little bit in these drone images, okay? So in order to be able to model, to work with these super complex patterns, we need to have very high resolution, and that gives us 100 million pixels per image. To process those 100 million pixels per image, today we'll work with NumPy, okay? But NumPy, let's get NumPy here. NumPy, just Google it, their page, is not an image processing library. NumPy is actually a vectorial processing library, a scientific library. So what NumPy does is what says in the package n-dimensional arrays. An array is just a list of data, usually stored in memory contiguously. So there are no gaps between the different components of your array, of your list, of your matrix. Okay, and matrix can be any sort of dimension. Okay, we will be working with 2D matrices, but 3D matrices are also useful in contexts like medical imaging, for example, when you're working with volume data like MRI or this sort of data. Okay. So NumPy is a library for scientific computation that focuses on arrays, on data that can be seen as different types of matrices, essentially. Okay. And it's very fast. That's what we will be using it. Let's go back to our computations. So matrices are NumPy's specialty, and we saw last time that images can be seen as matrices too. Because of that, images can be seen as NumPy vectors, NumPy arrays too. Okay. Okay. Here we are. So we already saw how to load some of the masks. Let's just define a couple of NumPy arrays to begin with. So one simple way to do that is just to call np array function. Okay, here we have an array that's made as a list of lists. Okay, and we can just print it, and we get in this case 2 times 3 type of matrix. Okay, so here we have something that it's essentially the same data type as our images, and we have made it by just defining the array. That's of course not completely useful because we are not going to be using our data from manual definition, but NumPy gives us many powerful tools to convert other data types to NumPy. For example, I can just define a list, in this case of strings, any data type that I want. I print its type and it's a list, of course, and then I can convert it to an array using np as array from my list, and then I get a NumPy array, and I can even print it in its list version and its a list and in its NumPy array version. Okay. And they look exactly the same, only the type is not the same. Okay, one we can give to NumPy and the other we can't. When OpenCV reads an image with imread, for example, that we have up here, okay. Sorry, now that I'm seeing, I don't know if this, of course, this one is small. Let's make it bigger again. Apologies, and please complain when these things happen. Okay, so bigger font again. So when we run these things, we get this NumPy array. When we run imread, we get type of data that OpenCV can manage, and that it's called an UMAT, but UMAT is directly compatible. It's exactly stored in the same way as NumPy arrays. So the OpenCV library is already designed to fit seamlessly with NumPy. Okay, so that will make us, it will make it much easier for us to process this type of data. Let's see a couple of examples. So for example, I can load an image. I didn't load my image initially. Let's load it, for example, here. My image, and I'm going to just read it from file. I'm going to just read mosaic, and then let's just use OS path join, and I'm going to be using my data folder. And then what? Let's load. We had been looking at S2, and here we want to load s2.jpg, for example. Okay. So I'm loading the mosaic that we saw before. I have data Sara here, S2, S2, and S2 JPEG. Okay, so I'm opening this file. I'm opening it with OpenCV, just like I do all the time. Okay, and I'm checking the dimensions. In this case, the dimensions, this is an OpenCV image and also an AMP array of size, what we saw before, 9945, 114303. By the way, when I checked it the other time, this was first and this was second, because as I think I already mentioned last time, OpenCV stores things in column major order, or instead of XY coordinates, YX coordinates. So be careful with that when you use OpenCV for your project, okay? Why did the OpenCV people decide to store everything in YX order instead of XY order? I don't know. Beats me. I honestly don't know why these people do these kind of weird things all the time. They have quite a few of them, okay? So remember, XY is off in OpenCV, YX is what rules, okay? And we have, we can see 1 pixel here and the same multiplication that we did before for the total number of pixels, okay? 1 pixel here, 255, 255, 255, okay? So we have 1 white pixel in that position for our RGB image. We can, of course, also load binary masks that we have seen before. And let's actually load a few masks for the next part. Let me copy these to here. So I will have a cell that loads all of the masks that I'm going to be using. So I'm going to be working with the masks for species 1, 2, and 3 inside 2. Okay, and I'm going to, let's define the paths first, and let's just load the mask with the readVM function here. Okay. By the way, let me show you, we can see if we are high, low on RAM, okay, by checking the resources folder here, okay? In this case, we are using about 40 gigas from our 107 gigas available in this free Colab machine. And then we are now occupying about 2 of the 12 gigas in the RAM from this same machine. This might be relevant for the third project. If you try to load too many things in memory, even with the GPU machines that we will be using in that project, you can change the runtime here and change the runtime type, and then you can choose different types. Both the CPU that we are using now and the T4 GPU are free. We will see more about this in project 3. But if you try to run too big a network or use too many images at the same time, you might run out of resources. If you start getting weird messages saying that the memory is full or that the GPU memory has crashed or something like that, check the resources tab, because you might be doing something wrong that's occupying too much memory space. Okay, so back to the description. We have been loading some images here, and we can even show them quite easily with Matplotlib, as we have been doing before, to have our images here conveniently visualized. Wait a second. Okay, finally. So we have a visualization here. Notice that I have been using imshow, and I have used 3 imshows in the same plot to show 3 things at the same time. And I have used alpha, which is a value that gives me transparency. So this is similar to what I was doing before with GIMP, but we can do it to create images in a matplotlib. You could even save this image as and download it if you want. Convenient way to visualize images. And here we see the position of the 3 different types of species that we have. One is darker and the other 2 a little bit lighter, so we know where each of them is. Okay. So we have masks, we have visualized them. Can we do something useful with NumPy? Oh, yes, we can. And as you can see, all of these images are pretty big, so even just visualizing them is a hassle, okay? NumPy has many useful functions. For example, one useful function is NPy unique, okay? Unique traverses one array, in our case, one image, and gives, as a result, all of the different values that can be found, but it gives each value just one time. Okay, so if I print, I don't even need to print it. Sorry, mask is not something, mask 1. So if I just call this, now NumPy is giving me the values in my first mask, okay? And I get a very interesting result. What are the unique values? What are the different values that my pixels have? Well, from 0 up to 255, which was to be expected, but not only those. So, oh, what happened here? I don't actually have a binary mask here, okay? I have a mask in grayscale that has actually quite a lot of the values in between. How did that happen? Well, probably when Sarah was doing her annotations, probably Sarah was using some of the paint tools in GIMP, okay? And those paint tools sometimes have diffuse values. Maybe Sarah erased some things where she had made mistakes and they were not erased perfectly. Maybe at some point she had some transparency turned on either her eraser or the annotation tool, okay? As a result, I have quite a lot of intermediate values, okay? I can even use, for example, npy_sum. npy_sum is a very convenient function that works on masks, okay? I can just do something like this, and this will give me a mask of the same size of my original image with true in the positions where my original image is equal to 41 and false in all of the rest. Okay, so if I want to count how many pixels have the 41 value in my mask, all I have to do is npy_sum and then give it the result of my previous computation. Okay, and this thing is fast. Okay, sorry, I can print this, and I will learn that I have exactly 2 pixels that have value 41 in my mask number 1. And with this, I have traversed all of these masks really, really quickly. Okay, I can even make this condition a little bit more complicated. I can, instead of making it just 41, I can make it bigger than 0. Okay, this one will, I have to print everything. Okay, now, okay, quite a lot of pixels that are bigger than 0. Okay, and I can even add complex conditions here. Let's see. The ones that are between 0 and 255. Okay. Okay, sorry, I have to do that. Let's not get into this now. I can do that if I want to know how many are between, so bigger than 0, but smaller than 255. I can do this in 2 steps. And I can use as Python is recommending here, any or all, but let's not get into this here. Okay, so this is the number of pixels that is bigger than 0, smaller than 255, than 255. Okay, smaller than maximum is the other one, and then I can just have a subtraction of the 2 things, and that will also work. Okay, so when my mask 1 is smaller than 255, okay, and then if I subtract these 2 things, I have the result that I wanted, which was sorry, actually what I want is to know the ones that are between 0 and 255. So here I have them all, and now I want to know the ones that are exactly 255. These are the ones. And what I wanted to know were the ones that were in between. Okay, now let me just finish this and I will explain it again because I didn't do a very good job. Now I will also explain why it was complaining about 0. Okay, sorry. Here we are. The ones that are between 0 and 255, not including any of those, are this. 12,544, which looks like a lot, but if we remember that we have 133 million pixels, these are really not that many. Okay, again, sorry, how did I do that? I wanted to just add the complex calculation here. I forgot that I need to use any and so on, and I don't want to get into that here. So let's just say that if I want to make complex calculation, my easiest bet is to go step by step. So I want to know how many pixels in my mask 1 are bigger than 0, so they are not black, but also not white. They are smaller than 255. So I just compute first the ones that are bigger than 0. And that's all the ones that I want, plus the ones that are exactly 255. And I don't want to count those. Okay, so if I want the number, if I want to see the number, I have to print it. If I do bigger than 0 equals print of this, I get the return value of the print function, which is none by default. Okay, so instead of that, I put it into this bigger than 0 variable, and then to take out those that I don't want to count, the ones that are exactly 255, I compute those separately. Okay, bottom line. NumPy allows me to count things about my mask really, really quickly. Not only that, it allows me to modify my mask too. Okay, so let's go. For example, I really don't want to bother too much with these non-white and not black pixels. These gray pixels are annoying me. Okay, so let me just get rid of them. How I'm going to do that? So let me call this auxiliary mask, and I'm going to, first of all, just copy mask 1. Okay. And for that, I use this copy, which is also an NumPy function that allows me to copy arrays really quickly. And here I'm again going over all the pixels in the array, but not one by one, but in parallel. And that runs very quickly again. That's why we are using NumPy vectors. And now I want to get rid of all of those annoying gray pixels. So I'm going to just say that mask aux of who? Of any pixel that's smaller than a given threshold. So let's define the threshold as, I don't know, 150, okay? So anything in mask 1 that's smaller than 150, I'm going to put to black in my new mask auxiliary that I'm created. Not only that, sorry, I should use the threshold here. I defined it for something, okay? Anything that is bigger or equal to the threshold is going to end up being 255. So white, okay? If I do this, now I have NPy unique of this mask aux, and I get an array that only has 0 and 255 values, okay? What did I do? Well, by creating these very quick masks that give me true in anything that holds this condition, and then using those masks to modify my mask. So I can give to one NumPy array an access index that's a full mask of itself too. Then I can modify the mask really, really quickly. Okay. I could do all of this with 4 loops. It would be simpler. I wouldn't need this extra abstraction step. Okay, I'm jumping one step into the abstract because I'm working here with all the pixels in my mask that hold this condition, for example. Okay, that's not working with concrete specific pixels that we had been doing, but one step higher up in the abstraction level. Okay, but by working with that, I can work really, really quickly. That's what we mean by seeing images as NumPy arrays, NumPy vectors. That's why we want to use those. Okay, we did a couple of calculations here. Let's make a couple more. For example, we did this with Matplotlib, and we use Matplotlib to show different masks in the same image with different levels of intensity. We can also do that just with NumPy. So let's define a new mask. Okay. So, for example, let's first of all well, we could put this into a function I don't think that we need to do that. I can, yeah, let's do that. It's really not difficult. So we can define a function called binarize, for example, that receives a mask and then copies it and it should also receive a threshold, and then it does exactly what we have just done. Okay, and then returns the mask, the auxiliary mask that we have created. Okay, if we do that, then we can define mask1 binarized as binarize of mask1, for example. Okay, and 150 we said. Let's define this as a threshold here. Okay. Yeah, invalid syntax because I have not completed this. Okay, but this worked. So let's define a binary version of mask 1, 2, and 3 really quickly. Okay, binary is not defined. I have not run the previous cell. Okay, so now I have these 3 binary versions of my original masks. Okay. Now I can combine these binary versions, so I don't have annoying gray values in between, into one single mask by just multiplying them. So how do I do that? For example, if I want to give them different values, I can just multiply them times scalar value. This is another thing that we can do with NumPy vectors. If I do this, actually I can do just that. Okay, and now I can call NumPy unique of new mask. What I have created is another mask that has the 0 just as it had before, but now 51, because that's the result of multiplying 255, which was the second value existing in my binarized mask, times 0.2. Okay. NumPy in this case has realized that it had 2 things of different sizes. One of them is a float value, float scalar, and the second one is a mask. So when I have said multiply these 2 things, NumPy has automatically understood, okay, so I have to make a mask that has the same size as this one, but only contains this exact value all the time. So it has created a mask with only 0.2 values, and then it has multiplied the 2 things pixel by pixel, element by element. Okay, I can continue this and give different values to the different masks that I have. Sorry, mask 2, and I'm just going to leave mask 3 alone. Okay, and I can plot that thing too. Yeah, mask 2, mask 3 is not what I want to write. I want to make them bin, because those were the ones that I had binarized. Yeah, I forgot here the multiplication, and that works. Okay, so again, I'm binarizing everything, and I'm trying to show actually a sub image, but I forgot to copy the definition of the xmin, xmax, ymin, ymax. Let's just copy them here now. And I will have a sub-image of something similar to what I did before. Before I used transparency with matplotlib. Here I'm using NumPy to create the submask with the binary values, okay? And I have created one of these submasks. I can also show, I don't know, much bigger value. Let's start this at 0. And I will get a bigger mask image here, okay? Okay, I can also show them, I'm also only getting, of course, black and white values now. I can do this same thing, but from the original masks if I want to, okay? So let's check here. Mask 1, mask 2, and mask 3, the non-binarized versions, and I will see a similar thing to what I did in the first case, okay? Similar type of grayscale representation of my 3 different masks. So what have we done here? Let's just sum up a little bit. We have used several NumPy functions on our images. So we have remembered that our images are matrices of pixels. We have used NumPy, which is a library to efficiently process arrays, or essentially matrices of many different dimensions. And we have used some of the functions from NumPy to do things quickly with our images. And we have seen that some of these things can be very useful. For example, first we started by using unique. That tells us what values we have in our matrix. And that gave us quite a lot of information and this idea that we had not properly a binary image. So we binarized it with this function, okay? We used these conditions. When I use one condition in one mask, I get a mask, a Boolean mask, a mask with true or false in each pixel of the same size as the array that I'm working with, as the image that I'm working with. And we use those to modify the image. In this case, we use them to transform every value under 150 to 0 and every value over 150 to 255, over or equal to 150 to 255. Then we saw that we could also just multiply NumPy array, in our case, an image times a number, and we use that to show a similar image to the one that we had seen before with the transference in matplotlib, okay? So now I'm going to give you 5 minutes because by this time this should be very, very simple. Sorry, we also use npsum, which is very important, okay? This creating a mask, a Boolean mask, and then doing something with it can also be used with npsum. If I want to know how many times something happens, I can express, if I can express that something as a condition with my image, then I can use npsum. See exactly how this works. npsum just adds the ones in one, sorry, not the ones, adds all the values in one mask, okay? And this mask 1 equals 255 is, as I said before, a Boolean mask. So it has true and false values, which sounds a little bit weird. Am I adding up true and false values? Yes, because true and false values in Python can also be read as true equals 1, false equals 0. That's a feature of the language, okay? So when I'm doing this, what I'm actually doing is first creating a mask, Boolean mask of the same size as this image mask that I had, okay? And I'm putting zeros or false whenever that pixel is not 255, and ones or true every time that pixel is 255. When I then sum the mask, I'm adding 1 for every true value and 0 for every false value. So I'm effectively counting how many times this happens. My mask is equal to 255. So let's use some of these, probably some, to do what we did before, count the black pixels in my mask number 1, okay? And we should get exactly this number, okay? Let's do that. I'm going to give you 5 minutes and then I'm going to move on because I'm a little bit pressed on time. Okay, so let's go for it. We're talking about how to count black pixels. So that one is pretty easy in NumPy, okay? If I want to count the black pixels in mask number 1, then, sorry, I should print this. I just need to sum the ones that are 0 in mask number 1. Okay. if I wanted to, sorry, is that what it should be? It's always a good idea to check your results if you're doing things in different ways, okay? So here I'm checking exactly black pixels, and yes, the number is exactly the same, okay? So that worked. So I can just do this, and I have done exactly the same thing as the long loop. And if you check the times, which you have to do for project number 2, they are pretty different, okay? Another thing that you have to do is use a map here. For those struggling with that part, don't worry too much about it, but you want to probably check something called product in either tools, okay? Ideally, you do not need to use any loop to use a map here. You also see that the benefit of the map is not so huge as it was in previous iterations, okay? This type of parallelization works better if you know that you're working in contiguous memory, as NumPy does, because it stores everything in contiguous memory, okay? By the way, this is what we had done with the loop, but as we had seen before, these are not grayscale values. So probably what I want to do is not exactly count zeros, but I want to probably count pixels that are smaller than a threshold, okay, and that the number changes. Decide whatever it is that you do, put it in your report, okay? As long as you justify what you're doing, it will be fine. If I wanted to do more complex calculations, like, for example, count the number of pixels that are the same that are equal into images, okay? So pixels equal into masks, okay? I could just check, shall I do it as a function? Yeah, mask 1, mask 2, or let me call them M1, M2. Let's give this a proper docstrings, which I didn't do before. Returns the pixels that have with equal value in M1, M2. Okay, so I can just do a double loop. M1, they are supposed to be the same shape. So for example, I could start with something like if M1 dot shape is different to M2 dot shape, and then here I could raise an exception masks with different size, for example, okay? Don't worry too much if you don't know what exceptions are. If you do, that's a way to do them in Python. You can just raise something and that will automatically work, okay? What's happening here? Oh yeah, equal val. I had forgotten the name of the function. Equal val. Yeah, okay. So, and here I can just do as I was doing before for the black pixels, count equals 0, and then here count plus equals 1 if when. I want to do it if my two masks have the same value. J equals M2 of Yj, Ij, sorry, then I count plus equals 1. Curious thing, I can do it this way, or I can also do something like because as I said before, true equals to 1, false equals to 0. I can say this, count plus equal and the condition. It will add 0 if the condition evaluates to false, and it will add 1 if the condition evaluates to true. Okay, so a shorter way to do that and to get rid of the if. Anyway, I'm not even going to call this function, okay? That would work if I wanted to compute how many pixels are equal in the two images. If I wanted to compute how many pixels are black in the two images, so I would need to say they are two equal, they both are equal, and at least one of them is 0, okay? Because then both of them will be. If I do that with NumPy, this is much faster. And by sum, for example, if I want to compute this for mask 1, mask 2, I can just add the condition here. Okay, again, I can print it. I get the same type of condition with NumPy. Okay, and I get the pixels that are equal in both masks. Okay, so equal in both masks NumPy. I could, of course, do this in function form. Because it's just one line, I will generally not even bother, okay? Sometimes I can add more complex combinations, more complex conditions here, which is fine, but sometimes the syntax is a little bit tricky, and sometimes I need a couple more steps. So for example, if I want to count how many pixels are black in both masks, then that's a little bit more involved with NumPy, but I can still do it. So for example, one thing that I can do is let me just copy one of the masks, mask 1, copy. And then with this here, I have another mask aux that has exactly the same values as mask 1. And I want to count the pixels that are black only, black both in masks 1 and mask 2. So one very simple thing to do here is to paint white all of the pixels that are white in mask 2. Okay? So if I do this, all the pixels that are white in mask 2, here I could do also, let's leave it like this. I could also take into account the threshold, okay? Here I put them at white. After I have done this, aux had exactly the same pixels as mask 1. So everything that's black in mask 1 is now black in aux. But now here I'm putting to white everything that's white in mask 2. So now aux contains first everything that was white or black in mask 2, but now everything that is white in mask 2 is also white here. So I am only leaving the pixels that are black at the same time in mask 1 and mask 2, okay? And now I can just print npSum of aux equals 0. And that gives me the pixels that are white, that are black at the same time in the two masks, okay? Let's just, so black in mask 1, mask 2 at the same time, okay? Everything black in, let's do a comment here. Black in aux is also black in mask 1. So here I have every black pixel in mask 1 and not one more. Paint white pixels that are not black in mask 2, okay? And now aux contains pixels that are black in both. So by using this type of NumPy calculation of quick mask modification, I can get very, very complex conditions going on. Okay, and yes, do have a look at any and all, and that will also give you a different way to make this type of modifications. Okay. Okay. So let's just let's quickly. I'm going to give you a couple of minutes because I don't have a lot of time for the combination. So let's try to detect overlap between two masks. That's something that we need also for project 2. Okay. So let's make a function that returns the number of pixels that are black in both masks in this case. Okay. So let's just a couple of minutes until 10:10 to turn this thing that we have just done into a function. Okay. So we can just put this into a function, which will perfectly work, but we can also skip ahead to the next part of the notebook that we are using for the explanation and use an accumulation mask. Okay, I'm just going to copy the function here directly. Instead of just having two masks, we can have a list of masks. So this masks here is a list. Okay, and what we are going to do here is just first define a NumPy mask using NumPy zeros, which is of course a mask that's full of the zero value of the same size as one of our masks. The first one is our list. Okay, here I could add again something like an exception. If len of masks equals 0, then raise an exception, empty mask list, for example, okay? If I wanted to be careful with that. If not, I'm just trusting my user to call the function properly, okay? In our context, not a problem. Professional applications probably do not trust your user so much. Okay, so I'm defining this accumulation mask, this mask where I will put all my information as zeros with a proper shape at the beginning. And then I'm just going to iterate over all of my masks. Again, I could use a map here to get rid of that. Not necessary, because I'm just doing one loop for each of my masks. And what I'm going to do is just add 1 to my accumulation mask for any value that's 0. Okay. So first step, I will read, if I call this, for example, with the 3 masks that I had before. Okay. First step, I'm going to be checking the pixels that are black, smaller than 150 in mask 1, and adding 1 to all of them. Second step, the same with mask 2. Third step, same with mask 3. End of my iteration, any pixel that has a 0 value in my accumulation mask basically has not been annotated in any of the masks. So that's, from my point of view, not a tree, or at least not a tree from species, what were they? 1, 2, or 3 inside 2, okay? If I have a 1, it means that it has been annotated in one of the masks. Which one? I don't know at the moment. In task number 4, I will want to know. In this case, I just want to know if there is some annotation or no annotation at all there. Okay. Finally, if I have 2 or 3, it means that that pixel has been annotated more than once. Okay. Sarah, when she was doing the different masks, maybe at the boundary of 2 different types of trees, she annotated the same pixel more than once. Maybe even there was a place where they were 3 different types of trees that were very close together, and one pixel got labeled 3 times. That happens. All of those things are manual. These kind of small imprecisions come with the territory and are absolutely unavoidable, and we need to account for them and to work with them, okay? I'm not sure if I said that before, but Sarah's work in all of this was terrific. So it was not that she was sloppy with her work or anything. It's just that humans annotating these kind of very, very small pixels, they are going to make mistakes. There is absolutely no going around this. I used to work in medical imaging a lot, and there these type of mistakes also happen all the time, okay? Okay, so this is a way in which we can see, our places where we have double annotation, okay? So I can even visualize that. I can, for example, just print, as we have in the notebook, the number of double annotation for our mask. Okay, the maximum value is 2. Here we are using another convenient NumPy function max, and then we can count the repetitions and so on. Okay, so this is a simple way to define and find double annotations, which will be useful for project number 2. Finally, some type of census annotation, because I'm just in my 5 final minutes. Okay, I can read some of my masks. Okay, for example, I'm going to go for sites 1, 2, 3, 4, 5, and species 1, 3, 8, and 9. Okay, different masks. And in each iteration of my loop, this is all in the images NumPy vector notebook. I'm just running it quite quickly here, but you can check it there. And I'm just, for every iteration, I'm reading one mask, species something something, sorry, site something something, species something something, and then I'm counting how many black pixels, how many pixels belong to that species in that site. Okay, and I have here the whole the whole information. I'm also creating a dictionary that has for each of the sites. For example, this is the part for site number 1. Okay, let's, for example, print that here. That would be a little bit easier to see. Has this thing gone small again? Settings, editor. No, it's still big. I don't know. I see it a little bit small. I'm going to make it bigger. Okay. Okay, the output is a little bit small. Okay, sorry about that. So I'm going to print dictionary idict of 1. Okay. Sorry, 1. Is it an integer? Yeah, sorry, I put it in string form, but here I'm making it an integer. Okay, so sorry, here I made it an integer. So in for key number 1, I have the following content. Okay, I have for species number 1 an integer with this value, integer from NumPy 64 bits. For species number 3, this other value. For species number 8, this other value, and this other value. And why have I stored things with like this dictionary that has integers as key and dictionaries as values? Okay, because that's the way Pandas likes to have its information. So if I store this in this type of dictionary, one key as every site, sorry, one site has every key in integer format, and then for each value, I have another dictionary with the key and the number of pixels for that species, then I get this kind of structure that I can just feed to Pandas. I can call the data frame from dict orientation index, and then I get a Pandas data frame. Okay. With that, I get a data frame that I can then use in any way I see fit. Okay. You can, of course, Google that, but I can just, for example, make the total per every site. I can just sum using Pandas my axis and get the total for every site. Or I can do, I can just get the total over the total, the percentage, sorry, the ratio over the total per site in every column. Okay, so I get different values in my data frame that can then be used to visualize and to interpret my data in different ways. Okay. And that's it for today. I don't have much more time. Today we have seen how NumPy allows us to interpret images as arrays and to process them very quickly. We have counted black pixels. We have counted pixels that are equal into images and black or just equal in general. And we have seen how to detect double annotation, which is something that's part of project number 2. So check it out. We have seen it a little bit quickly here, but you have more details on the notebook. Finally, we have seen how if I store things in this way, in this dictionary format way, I can just then fit everything to Pandas and create a data frame that I can then use. That's also part of another of the tasks. Here we finish today, but next week we will be checking out some of those more complicated tasks in project number 2. Okay, thank you everyone for listening, and here we end the session.